Hello students. I hope you people are all keeping well. So we did with the levers and mechanical advantage, velocity ratio and efficiency of levers, their classes and the numericals based on this. Now we are moving to the other part of the chapter, that is pulleys. Now what are pulleys? How do they work? What functions are there for the pulleys? All this we are going to study here. So without wasting any time, let's move further. So students, you can see here in the figure that there is a rod to hold the pulleys. Now what is a pulley? Pulley is a circular groove type of thing where you can put the rope around it or a string around it and you can bring some load up or you can move the load down by pulling or leaving the string. Okay. So here in the diagram you can see there is a rope which is going along the circular groove which is being maintained over there. And then it is going from the above groove to the lower one, then above again, then the lower one, and then it is going over there and fixed. That means it is fixed from one point and it is open or free from the other point. Now if you will pull the open part of the rope, obviously the load will rise higher. You can see over here. Now, this kind of pulley system is known as a block and tackle system. Above, the pulleys are all blocked, you can see. And the lower one is connected with the rope. So, this is known as a block and tackle system of the pulleys. Okay, so we move further. Now, coming on to the pulleys, we have the first kind of the pulley as a single fixed pulley, where we have only one pulley, only one groove, and that too it is fixed. Now in the diagram you can see there is a rod which is holding the pulley and there is a green part of the rod which is holding the pulley from the center. Now you can see a rope which is moving around that circular path. One side the load is hanging and one side you can pull the rope and that is the effort which you will apply from. Okay, so now you can see the pink part is the load. Then there is a tension in the string as the load is hanging over there. So there will be a tension maintained in the string. You know, when you will push or pull each other, there is a tension force which you have studied in class 9, which is a contact force. So when you are pulling something down, when you are holding or when you are stretching something, there is a tension maintained in the string, and here we will show the tension by T, by capital T. So tension in the string maintained is known as T over here. Now you can see the yellow part is the pulley. Then there is a string and effort E is being applied to pull the load above. Okay, so we move further. So we talk about the single fixed pulley. Now we will calculate the mechanical advantage, velocity ratio and the efficiency for the case of a single fixed pulley. Okay. Now mechanical advantage is load upon effort. We all know now. Now as you can see, load is being balanced by the tension in the string. Equal and opposite. Therefore, load is equal to T. Now, let us come to the effort arm. Can you see effort is also equal to T? Tension in the string maintained this side is equal to tension maintained in the string that side. Yes, by the tension by which you are pulling, the same tension, the load is also lifting above. Therefore, the tension is same both the sides of the string with the same force you are pulling, and therefore effort is also equal to T. Now, mechanical advantage is load upon effort. So, T and T cancel, and therefore it is 1. Fine. Now, the second one, if the effort E moves a distance D, if you are pulling the rope by a distance D, then how will the load move? If you are pulling the distance D, load will be moving with the same distance above, isn't it? It is only one single pulley over here. If you will move the distance of rope D, then it will shift up D. If you will move 2D, it will move up 2D. If you move 3D, it will move 3D. Okay. Or if you move 8 centimeter, it will move 8 centimeter. If you move 6 centimeter, it will move 6 centimeter. So load, distance moved by the load is equal to distance moved by the effort, and therefore velocity ratio is dl by de by dl, and which is d by d, and that is equal to 1. Okay, and efficiency is very easy. It is mechanical advantage upon velocity ratio, that is 1:1, and therefore it comes as 1 or 100%. Okay, so we move further. So now we have a single movable pulley. We have one pulley and that can move. So pulley can move up and down as only the rope which is there is supported by a rigid support, and the pulley can move. Okay, as you can see in the diagram here, the groove is having a rope, the groove of the pulley is having a rope around it, and as you move the rope above, as you apply effort to upward direction, the pulley will move up, and if you leave the rope, it will move down. Okay, and there is a rigid support from where the rope has been fixed from one end. Okay, now we have to study this single movable pulley in detail. That means we have to find out the mechanical advantage, velocity ratio, and the efficiency in case of a single movable pulley. Now you can see here that the single movable pulley has a center joint with a rod. From that rod, the load is hanging. So the load which is hanging over there is creating a tension in the string, that is tension T towards the rigid support side and tension T towards the effort side. So if I have to say, if I have to balance the things, so twice the tension, that means T plus T, is being balanced by L. L is balanced by T plus T, and that is L should be equal to 2T, whereas effort is only equal to T. Effort and tension are equal and opposite to each other in the effort arm, and therefore effort is equal to T. Tension, when you will pull something, there will be a tension maintained in the opposite direction in the string because it doesn't want to stretch and you are stretching it. Therefore, there will be a tension built up over there. So, effort is equal to tension. Now, we will calculate mechanical advantage and further things later on. Okay, so we move further. So now, students, you can see here that the single movable pulley is there. In the other diagram, I have just shown you an adjustment where a single movable pulley has been connected to a single fixed pulley. And that single fixed pulley is doing what? Is only changing the direction of effort. Till now, in movable pulley, you had to apply the effort upward. It is very inconvenient to apply an effort in upward direction. So that fixed pulley has been used to change the direction of the effort, and effort can be made in downward direction only. It is easy to pull something downward as compared to upward. Okay, so that is just a combination. So we are studying about the movable pulley. So let's see. So I was talking about that load here is being balanced by twice the tension, that is T plus T. So load is 2T, whereas effort is T. So mechanical advantage becomes load upon effort, that is 2T by T, and therefore it becomes a 2. Okay, so it is 2 over here. Okay, so mechanical advantage will be 2. So let's move further. So now we have something to understand clearly, students. Now see, velocity ratio is about the distance that is distance of effort from the fulcrum and distance of load from the fulcrum. Okay, that means how much has the effort moved and how much has the load moved. Okay, now if suppose load moves a distance x above, load is being pulled by a distance x. So what will be the amount, what will be the distance moved by the effort? Now see, if load is moving by x distance above, that means the string on the left and right both are moving x distance above, as the whole pulley is moving x distance above, isn't it? Now, x distance on left plus x distance on right. So that means the effort will move twice the distance what the load is moving, isn't it? Because you cannot have a loop towards the left rope. It will be all connected. So when you pull up load x above, it will be twice the movement of the effort above. Okay, so if load will move x distance above, effort will move twice the distance of what load has moved. So if I can say, in other words, effort moves twice the distance of what load is moving, and load moves half the distance what effort is moving. So if effort is moving x, load is moving x by 2, and such a machine is known as a force multiplier. Okay, you will apply half the strength and it will move twice. Okay, so let's see here velocity ratio. So we were talking about the movement of load. So dl will be de by 2. Distance moved by the load is half the distance moved by the effort. So distance moved by effort is de, and half the de is dl. So velocity ratio will become de by dl, and therefore de by de upon 2, and therefore velocity ratio also happens to come as 2. Mechanical advantage was 2, velocity ratio is also 2, and therefore efficiency is equal to mechanical advantage upon velocity ratio, and that comes 2 by 2, and that is 1. Okay, so that means efficiency is 100%. Now children, you all know that efficiency cannot be 100%. This is the case of a ideal machine where there is no friction in the bearings or certain other circumstances which come into the act. Okay, so this is the case of ideal machine, ideal pulley, single fixed pulley, single movable pulley, where efficiency is coming to 100%. But practically this is not possible. It will be less than the value of 1 or less than 100% efficiency. That means weight of the pulley, friction, various other things will act into the scene, and it will be less than 1. Okay, so we move further. Now here in this diagram, we can see I just made this just to compare fixed pulley with movable pulley. Now in fixed pulley, a fixed pulley changes the direction of force. You know, a fixed pulley has only been applied over there just to change the direction of effort to a convenient way. So a single fixed pulley changes the direction of force. However, it does not create a mechanical advantage. There is no mechanical advantage more than the velocity ratio, less than the velocity ratio. Hence, we say that it is only used for changing the direction of the effort. Now, movable pulley, the mechanical advantage of movable pulley is equal to the number of ropes that support the movable pulley. Now, you can see here number of in the pulley is having 2 ropes supporting it, and therefore they are saying that mechanical advantage will come as 2. Whereas above it will be 1 only. So movable pulley will have mechanical advantage equal to number of ropes which are holding the pulley. Okay, and this will be used as a force multiplier. Okay, now see, single pulley. We'll move further about the single pulley. Now, in single fixed pulley, as I mentioned, it is used to change the direction of effort to a convenient size. This pulley provides the user directional advantage. So, this is all written about that it only provides the directional advantage, nothing else. Okay, and for a single movable pulley, it will act as a force multiplier. We'll see in the other diagram. Now, in a single movable pulley, it will act as a force multiplier. As I mentioned in the before slide, that it will act as a force multiplier. That means if you apply effort E, load will move twice E. So you are working half what the load is working. So it is a force multiplier. Okay, children? So we move further. Okay? So students, now we have a difference between single fixed pulley and single movable pulley. It may be asked in examinations and you should know also. Although you know all the parts now as we have studied single fixed pulley and movable pulley in detail. So now the first one here is single fixed pulley is fixed to a rigid support. And single movable, it is not fixed to a rigid support. Only the rope which is there is fixed. The pulley can move. Okay. Second point, its ideal mechanical advantage is 1 in single fixed pulley, whereas its ideal mechanical advantage is 2. You know that load upon effort was coming as 2 because load was balancing twice the tension, and therefore it was coming as 2. Third, that its velocity ratio is 1 and the other one, its velocity ratio is 2. That means load upon effort and distance moved by effort to distance moved by load. I said if it will be half what the load has moved, it will be twice what the load has moved, and therefore it comes as 2. Okay. Now the fourth one, the weight of the pulley itself does not affect the mechanical advantage. So in fixed pulley they are talking about. In the fixed pulley, the weight of the pulley itself does not affect the mechanical advantage. Why? Because the pulley is fixed. We don't have to pull the pulley itself. We only have to pull the load. So it is only the effort applied only to pull up the load, not the pulley. Whereas in movable pulley, the weight of the pulley will also act, and therefore it will reduce the mechanical advantage from what it was in the ideal case. So weight of the pulley will act a part. Okay. Fifth, it is used to change the direction of effort from upward to downward. I said it is used to change the direction. The fixed pulley is only used to change the direction, whereas movable pulley is used as a force multiplier because you will apply effort and load will be done, more work will be done on the load. Okay. Sixth, the load moves in a direction opposite to the effort. Yes, obviously. Load moves up and effort moves down. In the case of fixed pulley, in the case of single movable pulley, both move above. If you don't apply a fixed pulley, then yes, you have to apply the effort in upward direction only, which is a very inconvenient way, and therefore load also moves above and effort also moves above in single movable pulley. Seventh, the axis of rotation does not move in space. That means the axis of rotation, that is a fulcrum which is fixed from the fixed rod, is fixed in case of a single fixed pulley, whereas in a movable pulley it moves. Okay, so these were some of the differences in single fixed pulley and single movable pulley. So you know it, you have understood also. So we move further. Okay, students. So now we have studied about a single fixed pulley, single movable pulley, and what are their functions. Now we are about to study combination of pulleys. How the pulleys which are single fixed or single movable have been taken and have been combined in a way so that they can be of some help in the machines. So we are going to study over here. You can see the diagrams. In one there is one fixed pulley and several movable pulleys, and the other one is a block and tackle system. So we are going to study one by one their advantages, their functions. Okay, so let's move further. So students, now we have the two kinds of combinations which we can have in pulleys. And what are they? Number one, using one fixed pulley and several movable pulleys. The first diagram, can you see? One pulley is fixed, but all pulleys are movable. Only the ropes are fixed, and therefore this is the combination of when one fixed pulley is there and several movable pulleys are there according to the case which we want. And second, using several fixed pulleys in two blocks in a block and tackle system. That means above and below, you can see the pulleys are connected to each other. You will see in the other diagrams also, and there is a load which is hanging, and this is known as a block and tackle system. They all are fixed with a strip which is joined from the center of the pulleys, and that fixes it, and so it is a block and tackle system. So we move further. So, students, now what we are going to study is, we are going to find out the mechanical advantage, the velocity ratio and efficiency in the case of the combination of pulleys. And we take the first kind of combination, that is several movable pulleys joined with a single fixed pulley. So we are going to study this. Okay. So now as you can see the diagram over here, there are three movable pulleys. Can you see? A, B, C are the movable pulleys, and D is the fixed pulley over there, which is fixed from the rigid support. And there are three strings which have been taken from the rigid support, and the third one goes around the fixed pulley also. Okay. Now see, load is hanging from A. A is balanced by T1 and T1. B is balanced by T2 and T2. That means the tensions in the string. C is balanced by T3 and T3. And D is balanced by the fixed rigid support. So it doesn't need anything to balance. And therefore, effort is only equal to T3. So effort applied is equal to the tension in the string, and that is T3. Okay. So now let us see what is the mechanical advantage, and for mechanical advantage we have to find out the load and effort in the same terms. So now let the load be L and effort be E. Okay. Now, as you can see here, load is balanced by twice the tension. So T1 plus T1. So that means 2T1 is equal to L. Or T1 is equal to L by 2. Okay. Now, second, we move to B now. Now, 2T2 is equal to T1. T2 plus T2 is equal to T1. T1 is been balancing T2 and T2. B is moving. So, pulley B is being balanced by 2T2 and therefore T1 is equal to 2T2. So, can we say T2 is equal to T1 upon 2? Yes. And T1 upon 2, actually T1 is what? L by 2. So now we have T1 by 2. So T1 by 2 will be L by 2 into 2. That means in the denominator we should have 4. L upon 2 to the power 2. That is 4. Okay. Now we go to T3. That is we move to the pulley C. T2 is balancing 2T3. So 2T3 is equal to T2 or T3 is equal to T2 by 2 or L by 2 to the power 3. Now you can see here there are 3 movable pulleys, so we have 2 to the power 3. If there would have been 4 movable pulleys, we will have L by 2 to the power 4. If we have 5, so L by 2 to the power 5. So here the power of 2 depends on the number of movable pulleys which we have in the combination. So in general, if I have to say what is the load, so we will say L, and what is the effort, so we will say load upon 2 to the power N, where N is the number of pulleys, number of movable pulleys in the system. Now let us find out the mechanical advantage. Now, mechanical advantage is load upon effort. Load will be L only. Effort we have calculated right now. Effort is equal to T3 and T3 we calculated as L by 2 cube. Therefore, load L upon effort E. So, L upon L by 2 cube and therefore answer is 2 cube. So, mechanical advantage is 2 cube. In general, it is 2 to the power n, where n is the number of movable pulleys. So please remember, in such a combination, mechanical advantage, you don't have to calculate all the time tension and load. You just have to remember this as a formula. Now, you have to remember that from where is it coming. You have to know this, but you know that load here is equal to L and effort is equal to L by 2 to the power n, where n is the number of movable pulleys over there. Hence, mechanical advantage comes to 2 to the power n. So we move further here, students. In this only we have velocity ratio now. Now this is something more to understand here. This is a difficult part. Now, velocity ratio depends on distance moved by effort to distance moved by load. Now, if load moves distance x, we studied while we were studying the movable pulley, we studied if load moves distance x, then pulley A will move up by 2x. Why? T1 will also move distance x. To T1 towards left will also move distance x, and T1 towards right will also move distance x. So x to this side and x to this side. So therefore, in total, B will move by twice x. Isn't it? A will move by twice of x. If load is moving x distance above, A will be moving by 2x distance above. Isn't it? So we will have the velocity ratio in case of A as 2 to the power 2 into x. Isn't it? 2 into x. Okay. Now let us come to B. Now you can see T1, if T1 is moving by 2x, then what will be the distance by which T2 is moving above? That is, B is moving above. So we will have 2x to this side and 2x to this side. That means 2x towards the left T2 and 2x towards the right T2. So in total, it is moving by 2 into 2x. That means 4x. Or we can say 2 to the power x. Similarly, when we come to point C, how much distance is C moving above if load is moving X? 4x to one side and 4x to the other side. So in total, it is 2 into 4x and that is 8x. Isn't it? Now, in total, the effort is moving. That means whatever C has moved above the same distance, the effort is moving, isn't it? So effort will move by 8x distance. So 8 times. Can you see? 8 times. Then how from where is we are getting 8? 2 to the power 3. 3 is what? Number of movable pulleys here. So when you are calculating velocity ratio, always remember when it is a movable pulley, velocity ratio, effort will move by twice 2 to the power n times, where n is the number of movable pulleys here. So velocity ratio we have to calculate. So effort is moving by 2 to the power 3x and load is moving by x. So x and x cancel. So we get velocity ratio also 2 to the power n, where n is the number of movable pulleys. Now efficiency is very easy. You can find it out. Mechanical advantage by velocity ratio, and that comes to 2 to the power n upon 2 to the power n, and that comes to 1. In case of a ideal machine, that is, it is 100%. Please, if you have not understood, ask me again. I can explain this again. Please be clear with this. Mechanical advantage, velocity ratio and efficiency in this case. Okay. So children, let's move further. Now students, we have block and tackle system here. Now the second kind of combination, we have the block and tackle system. So I have taken two diagrams. The first one is having 5 pulleys and the second one is having 4 pulleys. Okay. Now we have to find out the mechanical advantage, velocity ratio and efficiency in these cases. Now see, load will be NT. You can see the red tensions over there. I have marked with T. That is the red ink. So T is showing the tension in the string. You can enlarge the image and you can see that tensions in the string is T. So as many strings are there, those many tensions are there. So load is being balanced by NT, where N is the number of pulleys over there. So in the first case, L is equal to 5T, and in the second case, L is equal to 4T. Okay, so L will always be equal to, load is balanced by the number of pulleys over there in a block and tackle system. Please remember. Okay. Now, an effort will always be equal to the tension in the rope. So that means one side, by the force by which you are pulling the string, the same tension is created in the string in the opposite direction, and therefore effort is always equal to T. Now mechanical advantage will be L by E. So that is NT upon T, where N is the number of pulleys over there. So T and T cancel, so we get mechanical advantage as 1. Now, velocity ratio, that means distance moved by effort to distance moved by load. Now, if load moves a distance D up, then what is the distance moved by effort? N times of D. Now, this is not a balancing, this is not a movable pulley, no? So, if load is moving X distance, effort will move, as many movable pulleys are there, those many times X. So 5X in the first case and 4X in the second case. So if load moves a distance D, effort moves ND, where N is the number of pulleys. Therefore, velocity ratio is equal to ND upon D, and that comes to N. Therefore, efficiency is equal to mechanical advantage upon velocity ratio, that is N by N, that is 1 and 100%. That means in ideal conditions, where there is no friction, no this thing, then you will have the efficiency of block and tackle system as 1 or 100%. This is the ideal situation, okay? So let's move further. Now students, you studied about combination of pulleys and how to calculate the mechanical advantage, velocity ratio and efficiency in both the cases. Now we are going to study that pulleys are only force multipliers. Which pulleys? The combination of pulleys. The movable pulleys are only force multipliers. There is no gain in energy in these cases. In the cases of pulleys, we don't have any gain in energy. Either it is a force multiplier or it will only change the direction. It does not gain in energy. Why? We will see later now. Work done by effort, that is the input energy. Work done is force into displacement, you know. So in the case of effort, it will be effort into distance moved by the effort. So let the effort be E. So distance moved by the effort will be ND. In the case of the block and tackle system, where effort is moving, N times of what load is moving. Okay. So E into ND. So the product comes as NED. Work done by the load, so load into distance moved by load, so load into D. So load is what? N times of E. Whatever is load, whatever is effort, N times of the effort is load, isn't it? So NE into D. Again, we have NED here. So when output energy is equal to input energy, there is no energy gain in the machine, and hence we say that pulleys are only force multipliers. There is no gain in energy in the pulleys. Okay, so we move further. Now this one is the last part of the chapter. Here what we are showing is, we are showing that what is the effect of weight on the pulleys. And the movable pulleys, in the fixed pulley there is no effect. But in the movable pulleys, what is the effect of weight of the pulleys on the mechanical advantage, velocity ratio and efficiency of the machine? Now, let there be a system of n pulleys. Suppose there are n number of pulleys and W be the total weight of the lower block of the pulleys. That means all the pulleys which are over there which can move and their weight. So their weight will obviously act in the load. So whatever is the load, when you are pulling something, when you are applying effort, you are applying the effort to pull up the pulleys also, which are movable. You have to pull up their weight. So total load will be the load which is there and the weight of the pulleys. So we take W as the total weight of the pulleys here. Okay. So in the balanced position, when everything is balanced in the block and tackle system, effort is equal to T, tension, and load plus weight. That means the total weight now which you have to pull by the effort which you have to apply. So load plus W is equal to NT. Yes. Obviously, load was equal to N times of T. Number of pulleys which were there, the load was that many times of the tension. Now we have W also. The weight now becomes load plus W is equal to NT in the balanced position. Now when this is the case, so W moves to the other side, so L is equal to NT minus W, and NT, T is equal to E, so we can write it as NE. So NE minus W is equal to load. Now mechanical advantage is equal to load upon effort. So NE minus W upon E. So it comes as N minus W by E. Now here you can see, just because of the weight of the pulleys, the mechanical advantage is reduced from N to N minus W by E. So the reducing part which is there is W by E. So mechanical advantage reduces by W by E. Hence, mechanical advantage is less than the ideal value of N. Velocity ratio does not change because it is the distance moved by effort to distance moved by load. So it doesn't change whether it is fixed or movable or there is a weight or not. When you are applying effort, it moves the same distance. Hence, velocity ratio does not have any change. Okay. We are going to find out efficiency in the other slide now. Now, we just now calculated the mechanical advantage N minus W by E, and velocity ratio remains N only. Therefore, efficiency becomes 1 minus W by NE, because N minus W by E when divided by N will become 1 minus W by NE. Thus, efficiency is reduced due to the weight of the pulleys. More is the weight, less is the efficiency. That is very obvious. Now, for greater efficiency, the pulleys should be as light as possible and friction in the bearings of the pulley should be minimized by using lubricants. Okay, these are the two things which we have to notice while putting up the pulleys, that it should be massless. That means it should be as light as possible and there should be lubricants used so that the friction in the bearings is reduced, is minimized. So this was all about pulleys, students. We will take up the numericals next class. So please try to understand, and if you have any problem, please do ask. Try to do things properly, students. Please keep yourself managed, well managed. This is a difficult time and you have to cope up with these things. Okay? So take care. Thank you. Bye-bye.